Welcome to this webinar on Introduction to Ecosystem Modeling. And during this webinar, I will try to guide you through some of the basic understanding of ecosystem modeling, or as I would prefer to call it, biogeochemical modeling. And we will also be going through some of the DHI software, the MyEcolab tool, and learn a little bit about the fundamentals of MyEcolab and the possibilities of ecosystem modeling. So you will get something from this webinar about why MyEcolab is the tool for ecological modeling, and I will provide you with some examples of where we have applied Ecolab and ecosystem modeling, and I will also guide you a little bit about some of the pitfalls of ecosystem modeling. So I'm Anders Eriksen, and I have more than 20 years of experience of ecosystem modeling. I'm a Master of Science in Environmental Engineering, and at the moment I'm a Sales and Senior Project Manager at DHI in our Ecological and Environmental Department. I started working with models of rivers and lakes, but over the last many years, I've mainly been working in marine waters with the focus on the Baltic Sea. It doesn't mean that I'm not aware of the systems outside the Baltic Sea. I have also been modeling in tropical waters like the Pimperma Estuary in Australia and Singapore waters. So I'm familiar with modeling in both temperate waters and tropical waters and some of the different challenges between the different systems. DHI, very briefly, if you do not know us, we have been working with water for more than 50 years and in over 140 countries. We have offices in more than 30 countries and work in every kind of surface water or water-related environment. So it's for water distribution, industries, aquaculture, reservoirs, sewers, marine waters, flooding, and health and safety. I have made the marine water colored here because most of my experience goes with that one. I know something about modeling other surface waters, but you have specific questions for wetlands or groundwater, I will try to do my best, or at least I can guide you afterwards to somebody who knows. So today, the focus is on the water environment, ecosystem modeling using MyEcolab. Ecolab actually goes with most of the DHI software, which is very nice to know for you at least. So today, for the agenda, we will go through some different kinds of modeling, ecosystem models. What are the differences and what kind of modeling are we applying? There will be a little bit about MyEcolab, just in short. What can you expect from it, how to work with it, and then we'll go through some typical applications and a few examples. So this is setting the scene. Before we get started, I think it's important to just have a little bit about what is a model, and this actually doesn't only apply to water quality modeling or ecosystem modeling, but goes for all kinds of models. And that is very important to remember that a model is a simplified, limited, and pragmatic reproduction of the reality. So a model is actually characterized to be an abstract reproduction. The reproduction is simplified. It just covers the relevant and necessary informations. It is limited and pragmatic, meaning that it is designed to address specific questions and can probably not answer questions beyond the scope. And this is actually one of the things that I will return to during the presentation. That is, modeling is also or very much about choosing the right model for the right questions and issues. I have seen too many examples where a model has been used which is not suited to answer the questions that is actually used for. And then if you have a valid or chosen the right model, and it's a robust model, you have a valid solution or tool that can lead you to a number of hopefully correct answers. So why do we need models? Well, models can be used for a number of different things. It's very, very good and strong tool for testing hypotheses. So if you have an idea that some processes or the factors influences the ecosystem to a high degree, you can actually build a model and then test if this is the case or not. It's also an intelligent interpolation or extrapolation tool. So you can interpolate between measurement, or you can interpolate in time, and you can extrapolate doing scenarios to other situations, other nutrient reduction scenarios or whatsoever. But you should always remember that to use the model to an extent where it's actually not it's not valid anymore. It's also a very, very strong tool when you want to do budgets, mass budgets. So you can have a model, and then you can actually summarize how many tons of nutrient entering a specific water body, how much is leaving it, how much is turned around inside that. So as a budgeting tool, it's also a very, very important one. And you can use it for quantification. So quantification is basically if you do a scenario, for instance, and you can look at the difference between your baseline and your scenario, you have an idea of what the change you are implying in the model. Could be a change in nutrient loadings, or it could be after constructing a dam or a harbor or whatever. How big an impact have I actually experienced? And then it's a management tool. So you can use it in many ways for setting targets and guidelines for industries or whatever. And I will have a few examples of some of those later on. Which kind of models does actually exist when you do ecological modeling or water quality modeling? And there's a number of different kinds of models. I can see there's a number of questions coming in. I will take the questions in the end, just as you are not afraid that I do not see them, but at the moment they are coming a lot, so we will take them in the end. Sorry, but what kind of models? There is a number of different models for ecological modeling and or water quality modeling. I will not touch upon all. I will give a few examples on process models by geochemical models or individual agent-based models, and then the stochastic models and population models. And then there's also other models, but these are kind of the standard ones. So if we look at some of the model, process or biogeochemical models, and these are the ones that I will spend the time on today, they are defined by models describing the fate of mass or concentrations due to associated processes. And it's basically what we refer to as an Eulerian model approach. So for instance, you have here an example, which is a variable. So the change in variable over time is a process adding or process removing and so on. So there can be a number of different processes. And if you look at the image behind, which is a macroalgae of some kind, that could, for instance, be the change in biomass carbon over time, would be a primary production adding to the biomass. There would be a respiration removing. There could be grazers of some kind, snails, whatever, feeding on the leaves. And then there could be a leaf loss. And leaf loss could be a number of different things, maybe even coming from waves or physical things, or it could be a seasonal thing, so it drops leaves or shoots at the end of the season or whatever. And primary production here, that would may be dependent on a number of factors like light and temperature, nitrogen and phosphorus. Respiration would be dependent on the standing biomass and temperatures. Grazing from different kinds of snails and fauna or whatever. And the leaf loss, as I said, could be due to temperatures, physical stress or whatever. These kind of models are the ones that we will, I'm talking about today, doing the biogeochemical model or the Eulerian approach. and this is very suitable for Mike Ecolab. There's also another kind of model, which is individual or agent-based models. And here the definition is a model describing the autonomic behavior and state of agents, objects, or individuals. It's also known as the Lagrangian model approach. So the Lagrangian model approach, here is the important word, the autonomic behavior and state of agents. So we use this software, which is called the agent-based ABM lab, to model agents that move due to a number of predefined rules. So it's a rule-based model. And here's an example of array, and you provide rules to this agent, and then it adds a number of vectors that you sum up for every time step, and that actually defines where the agent is then going. So it could be something that we have used for modeling the migration of humpback whales, humpback whale, which is in the image, or yeah. And there's also a webinar coming up on this one. If this is the kind of model that you're also interested in, there will be a webinar coming up very soon here at DHI as well. And then there's one thing that we can do, because this is working exactly is in the same software as the Mike Ecolab. So there's actually a feedback between the two kinds. So you can have like zooplankton modeled in Ecolab, and then you can model fish with the agent-based model, and then they can interact, so the fish can actually eat from the zooplankton. And then there's a link between the Lagrangian and the Eulerian model approach. I will not go into more details about that. There is 2 papers here that if you're interested in that, you can see how we have integrated those parts. The first paper is on modeling eelgrass in a shallow estuary in Denmark, and it's affected by macroalgae attached to stones. So the stones moving around with the macroalgae is done in the agent-based model, whereas the eelgrass meadows are modeled in the Ecolab. On the other side, or the other paper here, it's on also eelgrass, but here it's the seeds that are modeled by the agent base. So we model specific seeds and the spreading of those to see where they will start providing new eelgrass meadows using the agent-based model, and then the growth in the Ecolab. The other 2 kind of models that I was just mentioned is like stochastic models or statistical models. They are defined as regression models. This is something that can be done in various different and ways and be more or less sophisticated. It could be a linear regression in Excel, but it could also be a number of other statistical models. And then there is population models, which is typically describe the state of a population, and they're typically matrix models. These are not something that I will go into details in at all, but just to say that there's a number of different models when we talk about ecosystem modeling. So, Ecolab in short. I know this is a lot about Ecolab as well, but you need a good software to get going and get started with ecosystem modeling. And we work with Ecolab, and Ecolab is an easy, open, and flexible equation solver, and it's linked to almost all of the physical DHI software models. So it goes for Mike 3, which is a 3-dimensional model. It goes for the groundwater. It goes for rivers and urban systems. And then so you have all the water going around with the physical model, and then you add on the biogeochemical model or the Ecolab, which is then basically taking care of the processes. As I mentioned earlier, a model is a simplified, limited, and pragmatic reproduction. It only covers the relevant and necessary information, and it's designed to address specific questions. So the way you work with an ecosystem model as such is that first you start by analyzing the project that you're going to assess and the data collected. So project analysis and data collection before getting started with a model, always spend time on doing that. If you're working with Ecolab, for instance, you now come to the sense where you can choose a model. In Ecolab, we are using the term template of a model. There is a number of predefined templates that comes with the software. So you can start by picking one of those. And then you actually set up and run the model. And the setup is basically applying information on the bathymetries or the river network. It's bed shear stress. It's physical forcings like wind, solar radiation, or whatever. Input from tributaries or point sources or whatever. So here you set up and run the model, and then you look at the results, compare them to measurements, and if the results are fine, they comply with the measurement within a certain restrictions, then you can say, okay, I have a solution, and I can start doing, for instance, scenarios or testing my hypothesis, and then work with the model as such. However, if the results are not okay, then you should ask yourself, is that because my theory is not okay? If my theory is not okay, then I have to go back to test my hypothesis, my theory about the system. I might be able to pick a new template. If there's not an existing template that applied to the problem at hand, then you should consider altering an existing template or building a new model. So there's an ecological model development. And then you go back to the setup and run the model, look at the results, test the theory. If the theory is okay, it could be just a matter of calibration. Calibration being where you change the constants and rates to make the model fit the measurements. And then there is a lot of interaction or iterative process going around checking the results, checking the theory, do the calibration, and so on until you have a solution that you're happy about. So this is how you should work with any kind of ecosystem model, basically. The way we have implemented ecosystem model at DHI is we have models describing the physical parts. So that is a model that is provided by bathymetry, wind, air temperature, and point sources, freshwater input, etc. Outputs information on the water level, current, and transport, salinities, and water temperatures. So that's the hydrodynamic model. Then there is an advection dispersion module. And that is basically provided by input of concentrations in rivers and point sources, initial values and boundaries, and the output of that one would be mixing, transport, and concentration at any given point in time and space, or whatever you're modeling. If it's a water, pelagic component, of course. And then we have the Ecolab, and or the ecological model. And that is basically, here you provide a number of equations that actually change the concentration. So you have the hydrodynamic, you do the transport, advection, dispersion module, and then you change the concentrations due to a number of different processes. That could be, for instance, the primary production, as I mentioned earlier. So based on nutrient inputs and or availability in the water phase and solar radiation, there will be a primary production that changes the concentrations. So the ecosystem model could be something that you do yourself. It's a predefined model, and forcing could be solar radiations, and outputs are processes like primary production, water transparency, concentrations of specific model parameters. And it's the latter that we often use together with scenarios to assess whether an ecological status will change or not. And then you have the model results as input to an impact assessment. So this is how it looks. My Ecolab is, as I mentioned, an open and generic equation solver. It goes with all. It's a Ecolab solver that solves system differential equations describing physical, chemical, and/or biological interactions. It's applicable with almost all the DSI model suite, ranging from groundwater, rivers, urban, as well as coastal and offshore models. Yep. And it's designed to develop assessing water quality issues. It can be used for a broader extent, but it's for you to use your imagination for that. So basically, there is a number of things to the left: state variables, constants, forcings, auxiliary variables, and processes, derived output. I will not go through all those. There will be a training course at a later stage if you're interested in that. But just an example. So you press the state variable. Here it's an example of dissolved oxygen. And the dissolved oxygen, that's the state variable. And here you have the equation. There's a number of predefined things going in as well, as you can see above the red arrow. But here we just see that what impacts the oxygen concentration at every time step. Well, that's basically reaeration. It could be photosynthesis. It could be a respiration due to plants. It could be BOD decay, some sediment oxygen demand, and maybe something about lithifications. So this is just an example. These are different things that impacts dissolved oxygen, and there can be more or there can be less depending on the complexity of the model that you're choosing. And then you go to, so that was actually state variables. In state variables, you can only access processes. When you have to define the processes afterwards, you basically, that's where you do all the math. Here I've taken the example of BOD degradation, and that's governed by a decay rate, which is basically could be at 20 degrees Celsius, defined by 20 degrees Celsius. There will be a temperature correction. There will be the BOD concentration should go in. There will be an oxygen limitation. So if there's no oxygen left, cannot consume anything else. And here we use a number of predefined and obvious, often used expressions from literature. So this is just an example of how we work with Ecolab. What I just started to mention is that there is a number of predefined templates in the software that you can always start with. But it's very, very important before you start going that you kind of analyze what kind of a system are you looking at. So there's a number of things and questions you need to assess before initiating modeling. And I have been saying that before, I will say it again, it's all about choosing the right model to the solution and ecosystem at hand. Lakes, for instance, and especially shallow lakes, they are very, very often quite difficult to model because there is, and it goes also for other kinds of systems, but it's very pronounced in shallow lakes. There's a very, very delicate interaction between the benthic compartments and the pelagic compartments. That's between the sediments and the water phase, and if there is any plants, vegetation or whatever, or if there's no vegetation. Rivers often does not have significant primary production and basically requires a decay model. Marine waters is, as lakes, dependent on boundaries and internal processes. And all these things imply impacts which kind of a model you should choose in the end. So first of all, it's important to see, is it a river, is it a lake, a marine area, and if it's marine, is it coastal or offshore? Depth is also important. I mean, it might not be, or it is important for the system as such, especially if there is a stratified system, then choosing a 2D model will not be sufficient. It has to be a 3D model, or at least a profile model, I mean a box model with more layers. Stratification often is affected by a permanent or periodic oxygen depletion, and you should have both a physical model and a biochemical model that can apply those if this is important. The environmental endpoint here is also very important. Are you evaluating the decay of a substance like bacteria or BOD? Then you can look, then the introduction of internal processes might not be important. If, on the other hand, internal processes is important, it should be maybe an algae growth model. So it's not just decaying BOD, it's also releasing nutrient that then becomes to new algae growth. And then it's very, very important that you choose a model that can handle those things and not just decaying or degrading organic material and nutrients. Model complexity, at best, you should take a model that only handles the number of state variables you need. So you don't want to have a too complex model. It impacts runtime, it impacts calibration, the difficulties. But on the other hand, choosing a too simple model can be very, very crucial and can result in wrong conclusions. So I mean, don't choose a too complex model, but definitely don't go too simple as well. And then climate is important. So most biological processes are influenced by water temperatures, and many models uses an Arrhenius or an exponential temperature expressions. So if you are using a model developed for temperate waters in a tropical environment, then you can really speed up processes undesirable. So that's just a small remark. As I mentioned, there's a number of templates available already. These can be used directly, or they can be altered through the template. We have generic templates like bacteria. That's basically a decay of Enterococci or E. coli. Heavy metals, toxic substance, and algae growth models or eutrophication models. So these are all generic. They are applicable for all surface waters, I would say. It might be unwise to use an algae growth model for a smaller river, as algae growth is not considered very important in those, but it's not providing you with wrong answers eventually. Then we have some BOD, DO nutrients in a number of different variations that goes with river modelers. And we have some intermediate models that can actually has some BOD, DO coupled to a simple algae growth model. But I would still advise you to go for the more complex algae growth model if that's the way you want to go. All template comes with a scientific documentation, and there's step-by-step guides available if this is something that you want to explore in more details. Typical applications, we have here a bathing water quality model set up for Copenhagen Harbor. Copenhagen Harbor is basically so clean now that it's used for swimmers, but sometimes it's deteriorated by CSOs or combined sewage outfalls, and we have used models to assess this. These kind of models is mostly used for assessing point and non-point pollution, evaluation of wastewater treatment plants, or the outfalls of combined sewage outfalls. Just a quick example here. In 2010, we had the first Copenhagen Challenge, triathlon event in Copenhagen. The day before, unfortunately, we had a shower or a heavy rainfall, and most of Copenhagen was flooded, and a number of sewage outfalls were activated. And here you see Copenhagen is, or you see Zealand on the photo on the left, and the Amager Beach Park is on the upper left corner, and just below you see the green route where the swimmers were swimming, and on the right you see E. coli concentrations developing outside Copenhagen and also entering the lagoon. And basically there were a investigation afterwards looking at if the swimmers have been impacted by those sewage outfall. They were basically swimming in the diluted sewage water. And what you see here is the bars are starting groups, and it's how many percent of the starting group. No, the bars are the concentrations, the average concentrations on E. coli, which you see on the right y-axis, and the black line is the amount in percentages of the different starting groups that got sick. So beside the first one, there's a clear tendency: the more bacteria they meet, the more sick they get. Getting from starting group, 65% of all the swimmers actually had some stomach infection afterwards. There's a paper, if you're interested in that, describing this, because it was both modeled and we have a forecast telling about the bathing water quality around Copenhagen. It was spot on, but the ones organizing this event did not want to. They want to go through with it anyway. Toxic substance. There's a model that describes different kind of toxic substance. Here is basically dissolved metal, which get adsorbed or desorbed to some particulate material, organic or inorganic material, and there's a sedimentation and a resuspension. And it goes in the sediments as well, adsorbs and desorbs in the sediment, and then from the pore water there is a diffusion transfer between the water phase and the pore water in the sediments. So this model is basically used for impact assessments, evaluation of point sources and cooling water, evaluation of dredging and or sediment dumping sites. This kind of model exists, but we have just an example in a more very advanced example, coupled the adsorption and desorption to the eutrophication model. It's doable because you have the Ecolab and you can do your own models. So here you have adsorption, desorption on phytoplankton and particulate organic matter. The detritus, it's something we did for the Swedish nuclear waste deposit company, and there is a paper here as well. You can go through if interested in that one. If you're interested in some of these papers, please let me know afterwards. I think this will be recorded and available afterwards, so you can also have a look to see if you can search for it by yourself. Then there's classic water quality. These are most BOD-DO models. So they are DK models in various combination and complications. Here's an example from a river Yamuna in India. Everything is basically fine upstream New Delhi. Afterwards, we see a number of pollution point sources entering. There's a lot of foam, the seaweed upstream, this sluice, a lot of foam downstreams. There's no oxygen in the water. Here we have used the models. It's a river models and it's a BOD-DO model. The blue bar here is, or the blue line is the BOD. So it comes from a level of maybe 2 milligrams BOD per liter, reduced to almost zero. Then it meets a wastewater treatment plant. The red line is oxygen. So the oxygen goes from between 7 or 8 to 0, and that lasts for a few hundred kilometers maybe until it meets. It's back at normal concentrations, and the next outfall is entering. And these kind of models are well suited in rivers and can be used to assess changes in population density or treatment facilities. Then there is also the more complicated ecosystem models. Here's a very complicated one. It has 3 algae groups: diatoms, flagellates, and blue-green algae. It models chlorophyll, zooplankton, particulate and dissolved organic material, inorganic nutrients, dissolved oxygen. There's a sediment compartment, and there's different kind of benthic vegetation. This is a model that we have used together with the Danish EPA and in combination with the Water Framework Directive in Europe to assess good environmental stages and developing river basement management plans, setting targets for the marine areas on what to expect at what loadings, and it's something we have been doing for the second plan period, and we are redoing it as we speak. So the third generation would also be based on these kind of models. Here you can also see there is a scientific documentation which is also available on the internet. So what is modeling, ecosystem modeling about? Well, basically, it's about applying the right model. It's including the governing state variables and processes and the complexity needed. And it's about collecting and processing input data. Models are never better than the data you feed them. Observations are crucial, but in literature and expert judgment works where no data exists. And then it takes practice. And this is something that I would just state because it needs you to work with it. If it's something that you just do occasionally, you will forget. It has to be something that you do quite frequent to maintain potential skills.